Hello, I'm going to make a start on capacitors now, and this is quite a big topic, so I'm going to have to do this on a couple of videos. In this video, I'm going to go through the descriptive stuff just to get us started. So what capacitors are, what they can be used for, things like that. And then in the next video, I'll go through the maths. So start looking at the formulae that we use in order to describe how capacitors behave, in terms of current and voltage when they're hooked up to a circuit. So getting on then with a description. So first of all, well, what is a capacitor? Well, it's two metal plates which can be connected up to a circuit. So we've got a wire connecting to each one of the plates, and we're using these to store electric charge or to sense things that might be happening in a circuit or in the environment around the circuit. Now, between these two plates, we usually have a dielectric. Now, dielectric is an insulator that can be polarized. I mean, I'll get on to why this is useful in a bit, but we'll have some kind of material here, this insulator, which might be something like glass. It might be porcelain. In old capacitors, you used to get paper and things like that in between the plates. And I'll come back to that in a moment. But if we've got this setup then of our two metal plates with this gap where we've got no current flowing between the plates, if we put this capacitor into a circuit with DC current, so we've got our conventional current flowing, so of course that means our electrons are going the other way, we're going to start getting a build-up of electrons on the right-hand plate because all the electrons are going to start moving onto the plate, but they've got nowhere else to go. And we're going to get an absence of electrons on the left-hand plate because they all start leaving in order to continue off moving their way around the circuit. So we're getting this build-up of charge, opposite charges on either plate. And it's going to get more and more difficult to push these electrons onto the right-hand plate because, of course, we've already got a load of negative charge there. So you have to have more and more energy available to push more and more electrons on. So eventually it's just going to stop because there isn't going to be enough energy available to do the work to push more electrons onto that plate. So eventually you're going to end up just blocking the current, and the DC is going to stop, and you're going to end up having a fully charged up capacitor for a particular voltage. So the amount of charge that we've stored on the capacitor Q is going to then be proportional to the potential difference between the plates. Because of course we're going to have this potential difference because we've done a whole load of work on these electrons to force them onto an already negatively charged plate. So we've put a lot of energy into getting this set up. So there's a lot of electrical energy that's stored on the capacitor, and that potential difference between the two plates is in proportion to the amount of charge that we've stored on the capacitor. Now the constant of proportionality here, if we turn this into an equation, Q equals CV, which you may well be familiar with if you've already studied this, the constant here is the capacitance. This is measured in farads, named after Michael Faraday. And usually capacitance is pretty small. We rearrange this equation. You see you've got C is Q over V. This is the charge stored per unit potential difference. In the units that we use, typically, we're already looking here in terms of coulombs on electrons. Okay, we're going to have a lot of electrons stored, but we're already starting with a base of 10 to the minus 19 for order of magnitude for charge on an electron. Voltage, whatever that might be, even if you're just running off a volt or two, we're starting at a pretty low base here of this, very, very small number. And usually for capacitance, we're looking at things like microfarads by the time we've, actually worked through the sums on all of this. So, yeah, we're talking about small numbers in the system of units that we actually use. Capacitors, as I said earlier, can come in a real range of sizes. I mean, you can get tiny little ones in, nanotechnology and all this sort of thing. You can get capacitors like, well, on touch screens and things like that. I mean, they're so small you can't see them. But then you can get ones that are big enough that you can just pick them up. The one thing that really does affect it is the effect of voltage on the dielectric. So what this dielectric is doing is it's allowing us to store more charge on the capacitor plates. So we're getting a higher charge storage capacity by having this dielectric there. Because although, you know, it's insulating and it's blocking any current flow between the plates, which of course is what we need in order to get this potential difference between the plates, in order to store that charge, you know, in order to build up the energy that we're storing on these on this plate. So the dielectric is having that effect, you know, it's maintaining that insulating gap between the plates, but it's also polarizing, because that's what dielectrics do. So if the dielectric will align in this, you know, positive negative, this is how the atoms and molecules in the dielectric are going to align themselves. So we've got this positive side to the dielectric pointing towards the negative plate, and the negative side of the dielectric pointing to the positive plate. It just makes it easier. It's reducing the electric field between the plates, and it makes it easier to push more charge onto the plate. Because, you know, if we want to get another electron onto this negatively charged plate, well, we've got this positive set of charges sort of sitting behind it in the dielectric, which is just giving us a helping hand to get a bit more charge on there. So it makes it possible to store more charge. So the capacitance will go up if we've got this dielectric in between the plates of the capacitor. But of course, with insulators, they have a breakdown voltage. So there's going to be, if the voltage across the plates is sufficiently high, then it will start, the dielectric will start conducting. Essentially, you're going to start getting electrons ripped out of where they were quite happy being in the structure of this insulator. They're going to get ripped out of the structure, and you're going to start getting current flowing through the dielectric. It's no longer going to be insulating because we've hit this breakdown voltage. So if you hit a breakdown voltage, well, there's a couple of things you can do with this. Well, I mean, you can separate the plates more. So that's something. You can make the capacitor bigger all round. If you separate those plates by more, then you've got, you know, a lower potential gradient going between the two plates. Okay, you might still have the same potential difference, but it's acting over a larger range in space. So that can help. And then you have a bigger dielectric in there, and that will insulate better against the effect of the large potential difference. So you want to physically make the capacitor bigger with a larger lump of dielectric between the plates in order to protect against very high voltages. So, and then, you know, you'll see this, that you'll actually have some capacitors, you can just pick them up. They're, you know, they're big capacitors, you know, physically speaking. But yeah, so you've got this huge range in sizes of capacitors. So what do they actually get used for then? Energy storage is a big one. So they don't have the same energy density as a battery, but they can give energy very, very quickly. So they won't last for as long. You know, batteries, I mean, well, we know how long batteries can last for. They can last for hours, days, weeks, you know, whatever, depending on what battery that you've got. Capacitors aren't something that you're going to be relying on for a prolonged period of time, but the electrons are just there ready to go. So that is one difference. Another difference that they have with the batteries, they might not have the energy density, but they can discharge very, very quickly. You can have a problem with batteries if they discharge quickly, because it can end up damaging the structure of the battery. Capacitors, you don't get the same issue, or at least not the same extent of the issue. So these electrons are ready to go. You can get a very quick, short duration input of energy on demand. So it might be, you know, if you're changing a battery in something and there needs to be a backup supply of energy for a short period of time while you're taking a battery out, where the capacitor can fill in that gap. You might have something like a car stereo So you're not plugged into the mains or anything like that. You're mostly running it off of the battery of the car. But if you get to a particularly loud bit of the music and you need a sudden burst of energy, then a capacitor which has already been charged up, or a set of capacitors which have been charged up, can then quickly discharge to give you that extra bit of energy for a short period of time without putting extra load on the battery. So if you want a short burst of energy, capacitors are great. They can fill in those gaps. They can also be used for splitting AC and DC. So you might have an electricity supply which has got both AC and DC in it. And we saw in some of the circuit analysis videos that I've done that these things can overlap. You can superpose these different sources, these different power sources, and they can superpose on each other, and then they add up in order to create this sort of aggregated supply. So, and you can get that with AC and DC, which might be, you know, flowing down the same wire. Well, you might want to split these things out, and capacitors will block DC, but they'll allow AC to flow. We've already seen the effects of blocking DC, because if you've got DC, the current will flow until we no longer have the energy to force any more electrons onto the negative plate, in which case DC then stops. AC doesn't have the same problem because the current's always changing direction. So if you've started building up electrons on the right hand plate, well, it won't be long before the currents change direction and they'll all be off again. So the AC will keep on flowing because it's just going backwards and forwards, it's oscillating, but the DC will end up getting blocked. So it can be useful for that in certain more advanced circumstances. You can get voltage regulation using rectifier circuits. So this is another thing which is useful. And if you want to, rectifier circuits are when you're wanting to convert AC to DC, and then you might want to get a very smooth voltage. So what can happen with this is, so let's draw out a little rectifier circuit then. Actually, that's too long a line because I'm going to want to put a diode in. So say we've got our 230 volt AC supply that we get at home, and we want to turn this into DC. So let's have a diode to block one half of the DC, essentially. Put a sort of protective resistor in, put a capacitor in, and then we've got our V out over here, which we're connecting our appliance to. So we've started off with our AC, which is doing this. We've then got the diode there. So that's our AC. We've got our diode. Okay, that line, the axis is meant to be going through the middle. The diode is going to change that. So say we've just got the positive bits. So that's a start, but we've got these dead bits sitting here where there's nothing happening in between. But of course, once we've got the current flowing, this capacitor is going to start charging up. So we've got our current flowing, all this way. We're going to get our negative charges there. We're going to get our positives on this side. So that's all going to start building up. We're going to charge up our capacitor. Then we're going to get this dead bit because the diode is blocking this negative part here of the AC. So when that happens, the capacitor is then going to discharge. So we've got, some in this block here, we're now going to have the capacitor is going to discharge conventional current going in the same direction. So we're not changing anything here at these points here. We're still going to get a DC at this point. Because this discharge is going to sort of fill in these gaps to some extent. Okay, it's going to drop off because we're going to, when it initially starts discharging, we're going to have our maximum current as all of the electrons just run off of the plate. They all surge off, and it's going to, it's going to decrease the flow. It's like opening a floodgate of water. You get a surge, and it's just going to decrease over time. This is one of the things we're going to quantify in the next video when we get onto the maths. But you're going to start filling in these gaps between these AC peaks, these remnants that have been left by the diode. So you're getting something which is beginning to approximate DC here. Okay, it's got a ripple on it because now we're going to get something which is looking a bit like it's going to go down a bit and then up and then down a bit and then up and then down a bit and then up, because we're getting the AC peaks with the capacitor discharge in between. So you get this variation in the voltage, what they call a ripple voltage. So that can get smoothed out more and more. You know, if you've got multiple phases in this, you know, you can have triple phase AC supply. So you'll actually have, rather than just one of these AC curves, you'll have three of them. They'll all be slightly out of phase with each other. So you might have another one which is doing that, and then another one which is doing this. And you can see this is already smoothing it out quite a lot more, because then when you're getting the capacitor filling the gaps, it's not dropping off as much because it's only having to fill in for a shorter amount of time. So now our ripple is much smaller. You're still going to have a small ripple, but it's going to be fluctuating much more quickly and over a smaller range. Yeah, if you think of we don't get three-phase AC in our home supply, but if you're in something like heavy industry and you want a really, you know, much better regulated voltage, then you'll have this three-phase supply and you can get something much smoother. But even in you know, home supply, we're what, 50 hertz is the frequency of our home 230 AC 230 volt AC supply. So 50 hertz, okay, you're going to have these gaps in between. If you think we've got this gap here of half a cycle in between these peaks, so it's flickering off still pretty quickly, even when we've got our 50 hertz supply with just one AC phase in there. So yeah, the capacitors are really good for smoothing out that sort of thing with these rectifier circuits, filling in those gaps. They're also good for sensing. So anything which changes the capacitance of something is then going to change the potential difference across the plates. It's going to change the current that's flowing in and out of the capacitor. So something which is going to change our capacitance, our C value, can then be picked up by other parts of a sensing circuit and tell us things that are going on. So say you had a porous dielectric, then the capacitance might change with humidity. So we can use it as a humidity sensor. It could be that you put a capacitor inside a fuel tank. So if you've got some fuel level, which is partly covering the capacitor, then depending on how deep the capacitor is into the fuel, that will determine what value of C we're getting, and the capacitance has changed accordingly. Again, we can pick that up in a sensing circuit. You get capacitors in touch screens. You're actually making physical contact with the capacitors in the touch screen, changes their capacitance. You can then start sensing things. I mean, not all touch screens work in that way. Some of them are pressure related, but yeah, capacitors are a core part of these touch screens. So sensing circuits is another big part of what capacitors are used for. So yeah, they got a whole load of uses, which is why, I mean, they're just everywhere in electronics. So I think that sort of covered a quick broad brush description of what capacitors are, what they're used for. And then I'll get on to the next video. Let's get some maths behind all of this so we can start actually quantifying things and getting rigorous descriptions of voltages across capacitor plates and currents flowing in and out. So we can actually start seeing, well, what current are we going to get supplied by a capacitor when it's filling in these gaps in AC, or if we want to have our turbo boost on our car stereo or something like that. So yeah, that's coming up next.